From the beautiful studios of Way Happy, this is Mr. Meyer and 1-4, limits and their properties. All right, we've done a bunch of junk with limits now, and now we're going to move on to something called continuity, or to define if a function is continuous. Now, in the past, we've always said, oh, it's just when you can draw the graph without lifting your pencil, but we don't want to say that anymore. We kind of want to move it up now and try to use the definition. So the definition of continuous would be those three steps right there, right? And what are those three steps? Those three steps are that the function is defined at C. So whatever, if I want to be continuous over a certain point, let's say the point's 3, then we have to have a value for f of 3, right? There's got to be a y value when you plug 3 in. The limit has to exist, which means there has to be a limit, right? It has to exist at that number. So we now know there's a difference between limits and a difference between the value when you plug it in. So again, at 3, there has to be a limit. And the third step, probably the most important step, is that the limit has to equal the value when you evaluate it at that. And if that's true, then that point is continuous, or what we call continuous. And then we want to stretch that over to what we call an open interval from A to B, where everything in there is continuous, meaning every point from this point to that point, but not including those endpoints, because that's what we mean by the word open. So open means that we don't include those endpoints, but everything in between those endpoints, those are continuous points. And that would be true if the limit equals the value when you plug it in, right? So, and then off to the right, you see a couple of things I talk about not defined. You can see that on this first example here, on this one, I have a hole, right? That's a hole. The limit exists, but the function doesn't exist at that point. So therefore it can't be continuous. And I can't even get to number 1 doesn't even work. Number 2 does, but number 3, no go. And how about this second one, which we like to call a jump, right? This is another way of saying a jump. A jump is when the graph is cruising along, and see there's a filled in circle, so it exists there. So yay, step 1 works. Step 2 doesn't work because there's no limit. The left-hand limit, the limit doesn't exist from both sides. I can't make a guess. And then finally, the last one, showing you that you could have a point that exists somewhere. So you'd have a limit and you'd have a value, but because of those two things aren't the same, it has step 1, it has step 2, but it doesn't have step 3. And so don't forget, there's also infinite discontinuity, right? Where there's an asymptote. So if you had, a graph that takes off at some point and comes back, that's also a type of discontinuity because, the limit doesn't exist. It's not even defined at the point. So that's called infinite discontinuity or an asymptote. So you got a hole, you have a jump, and you have an asymptote. And again, those are the 3 types of discontinuity that we will always talk about. Now, just so you know, they fall into 2 categories. One that's called removable and the other is called not removable. And for us, the only type of removable discontinuity we will see ever is what's called a hole, right? So that is this example right here. When we have a hole, or maybe even this one, because it'll have a hole in the graph, but it exists somewhere else. When we have a hole in a graph, that is called removable discontinuity. And the way you can tell if it's removable or not is, could you fix it by just plugging in a single point? Like, could you put a point in somewhere? Like I can here, I can put a point right there, right? And now all of a sudden, that one's fixed. It's continuous. But I can't do that anywhere else. I can't come over here and put a point, right? Can't put a point there and be like, oh, look, it's fixed. No, there's nowhere to put a point. Or this one, I guess we could call this removable because I could put a point in there. So again, that special type of hole. So the way you tell is if you can fix it, and that's in the definition of removable, is if you can fix it with one little dot, then therefore that means it is a removable type. And if you can't fix it, then it's not removable. So let's look down here at continuity of this function, right? So if you look at example 1, and I want to talk about any of the discontinuities, or is it continuous maybe even? Let's find out. So if I look at this graph, I know that we have x cannot equal 0, right? Now that is a vertical asymptote, right? So that's that infinite discontinuity I was talking about. And so what does that mean? That means that, the function isn't even defined when x is 0. So we're not doing a point, but we're doing over a whole graph. So this one has a vertical asymptote. So it would be, what could we say? It would be, I could give you an interval that it's continuous from like negative infinity to 0. I could say from negative infinity to 0, it's continuous. And then and notice I didn't include 0. And then from 0 to infinity, it's continuous, because that's the interval where it's continuous, and that's open intervals, because that is where the graph is actually nice and smooth and pretty, right? Where it always has a limit and a value at a given point. All right, what about this guy right here? This again, I have something trouble at x equals 1, right? X cannot equal 1. So, but I know that this factors. I know this is x plus 1, x minus 1 over x minus 1. And good news, those factors could cancel, creating what we call a hole. Now, what does that mean? That means it's got removable discontinuity. By the way, this was non-removable. And now I got, on this one, I have removable, right? And what does that mean? That means that there's a hole. So what does this graph look like? It looks like just a regular old x plus 1 graph, but it's going to have a hole at 1. And so this one does have a hole or removable discontinuity. Where is it continuous? Well, it's continuous everywhere up to 1, right? And then after 1. So again, I could do that same thing I did before. If somebody asked me to give you an interval where it is continuous, an interval where it's continuous would be like negative infinity to 1 and then 1 to infinity. So that would be just an area that's an interval of where this graph actually exists. All right, what about C? C has a nice little property here where I want to know if it's continuous. I can see that it's got a line and a parabola. So that's telling me we have, a jump in there maybe. So what does a line look like? Well, a line goes like, up 1 and then up 1 over 1. So it looks like this. And then the parabola is a parabola that's up 1. It goes like this. Right? Oh, gosh, that's so funny that's so squiggly. And so what do you got? Well, according to this graph, you have the line when you're less than 0, but not including. So right here. And then you have the parabola when you're greater than 0, and it is including. So it goes like this. So this graph, to me, looks continuous the entire time. Every x value has a y value and nothing ever weird going on. So this would be actually continuous. It would just say it's continuous, right? That's a continuous function. And just like D, I know sine graphs, right? Sine graphs just go like that, and they are definitely, I guess that should go down here. They are definitely continuous everywhere they exist. Every point they exist, and the limit of that point would be the exact same. So there is my definition of continuity and explaining when something is continuous or not, and what intervals. This interval for continuity would be infinity, negative infinity to infinity. Same thing with this one. So all kind of neat stuff that we can talk about continuity. All right, let me ask you a question. I'll be right back. All right, nice work. Now let's look at this. Example 2 here, and what we're asking there is just left and right hand limits. We've kind of talked about it, but let's make sure that we're all in agreement here. And that you can take limits. The limit is at the point you have to check the left and the right hand side, and there's actually, we call that the right hand side and the left hand side. And sometimes we need to just look at one of those sides because the other side maybe doesn't exist, and that happens a lot in square roots. So look at example 2 where it says find the limit as it approaches -2 from the right. So I fired up Sheila and I graphed her, and you can see there in the middle, it's got the equation, and that's what the graph looks like. So if I approach -2 right here, -2, and then I approach it from the right side, you can see that it's closing in on 0. Even my table shows that. So that's when I'm asking you to say, what's the limit as x approaches -2? And I want to say from the right side, I put that little plus there. And then I could have the function here or whatever. And I ask you, where's that approaching? And looking at the graph, I could see it was approaching 0. And we could even plug in -2, right? We could plug -2 in, we could square it, we get 4, and 4 minus 4 is 0, and the square root of 0 is 0. So even plugging it in, we can see as you approach from the right side, we are going to get what we would call 0. All right. that kind of helps us really define limits even more, or the existence of limits is what they call it in Theorem 110. But if you see it, it says let f be a function, and let C be the C and L be real numbers. Then the limit of the function as x approaches C is L, and then here's the big part: if and only if the left-hand limit is L and the right-hand limit is L. So kind of what we've said, right? As long as the left side agrees and the right side agree, then that's your limit. And there it is. So left-hand limit, right-hand limit have to agree. Now there's some properties of continuity that we should talk about too. So we've got limits, we've got continuity going on. What kind of properties do we have to do of continuity? Well, we talked about continuity, and how you check it is the limits. Make sure it's continuous, right? Make sure it equals. Remember, you got to check the limit, and then you got to make sure it equals what you evaluate at that point. And then we get into properties of continuity, where if you have two functions that you know are continuous at a certain point, then you can multiply those things together, you can add them, or you can divide them, and that will still be continuous. So it doesn't matter. And then if you look to the right side over here, of all these things you guys already know that are continuous, there's all these different graphs that you already know are continuous because you've done them, you've dealt with them throughout the years, and you feel pretty good. If you combine that theorem and that, you've got a whole smoke of stuff that is continuous, right? Because you know that these graphs separately are continuous, and then this theorem says that if you put them together, they're continuous. Wow, heck, life is pretty good. So like, even look at this one then down here, f of x, x plus sine x, pretty goofy looking graph, scary, but you could tell it's continuous because x is, y equals x is continuous, y equals sine x is continuous, and when you add them together using that property, it'll tell you, hey, that's continuous also at every point. What about multiplying by a scalar, right? Tangent's a funny one, right? It has those weird asymptotes in there. So it's continuous on its domain. And so if you say on its domain, you're ruling out the asymptotes. And then if you multiply by 3, well, that's okay because that's just a scalar multiplier, and that's still going to be continuous. And even the last one, we know those are two continuous functions, and the only time we have to worry is when cosine is 0. And that would be the only time it would mess up its continuity. So that's just a little way of you can kind of worry about when things are continuous or when they aren't. I know the numerator is continuous, I know the denominator is, but once we divide it, just got to make sure it doesn't equal 0, and life is good. Now that makes it a little tricky too on composite function. Composite function, when you plug one into the other, you kind of have to check the one you're plugging in, and then when you put it into that other one, you can see if it's going to stay continuous, or at least worry about if it's not continuous at a certain point. All right, now let's look at example 3 here. Describe the interval on which the function is continuous. So we have this graph, right? F of x is sine of 1 over x from x is not 0, and then when x is 0, let's make the graph equal 0. All right, so remember, this is a composition of two functions. The 1 over x graph, which we know doesn't have a value at 0, and then sine, which is continuous. So we have to figure out what the heck is happening with that sine of 1 over x graph. So we know at 0, it's not continuous, right? But what value does it have? That's really what I want to know. Is this going to be a nice smooth value or what? Well, if you remember with the sine of 1 over x graph, it looks like, let's see, I can pull it up here on Desmos, and remember that it's this one that got really weird. And then when you zoom in, it just sits here and oscillates between 1 and -1, and it really doesn't matter how much you zoom in, you will always be bouncing back and forth between 1 and -1 constantly, as it just gets this big orange muck in here. And so because of that's going back and forth, we can't have, the limit did not exist. And because the limit didn't exist, because we couldn't get the left and right side to agree on anything, as it was constantly bouncing back and forth. Therefore, when we go back and look at this one, I have, it's bouncing between 1 and -1 the whole time. And then you're going to try to put me at 0 when I get closer to 0. There's no way I can be bouncing back and forth and then all of a sudden be there and say that you're continuous. So the bad news, this thing can't be continuous. It can be continuous from -infinity to 0, and then from 0 to infinity. But because of its bouncing back and forthness, all of a sudden it's going to jump to 0. That doesn't make sense. And so therefore it can't be a smooth, continuous graph. All right, that's it. Have a great day. Stay out of trouble, and I'll see you tomorrow. Stay happy.